for our next DE equation, what if it is now negative? So our DE is y double prime minus y is equals to 0. So I already plotted the y prime, and y double prime so that we can immediately substitute it. Then let's substitute. So our y double prime is n is equals to 2 n minus 1 c sub n x raised to n minus 2 minus our y is n is equals to 0 infinity c sub n times x raised to n is equal to 0. So just like before, we need to balance this equation because their bases are not the same. So we need to subtract 2 here and remain this in order for this to become n is equals to 0. So when we subtract, it will become 0. So when you subtract 2 here, we need to add 2 here. So it will become n plus 2, n plus 1, c sub n plus 2 times x, n minus 2 plus 2 is raised to n, minus, and just copy this, n is equals to 0, c sub n is equals to 0. Now they have the same bases, we can factor out the same terms. So the same terms is n is equals to 0 and x raised to n, and what's left is n plus 2, n plus 1, c sub n plus 2 minus c sub n equal to 0. So for this, in order for us to find the multiple numbers of n, we need to assume that x raised to n is not equal to 0. So that leaves us with this n plus 2, n plus 1 times c n plus 2 minus cn is equals to 0. When we factor out, or when we transpose this into this side of the equation and then divide it by this. So our recursion relation is c sub n plus 2 is equals to positive because it is negative cn all over n plus 2 n plus 1. So what's the difference from the first D that we made is our recursion relation now is positive. So now we will find the multiple numbers of n. Start with again n is equal to 0. So if n is equals to 0, cn plus 2 is c2 equals to c0 all over 2 times 1 is 2 times 1. I made it 2 times 1 because later we can assume that, so we can easily assume what factorial it is. So we can say that is equals to 0 all over 2 factorial. So if n is equals to 1, cn plus 2 is c3 equals to c1 all over 1 plus 2 is 3 times 2. So 3 times 2 equals to c1, or you can say 3 factorial. Next is n is equals to 2. So if n is equals to 2, we have C4 is equals to C2 all over 2 plus 2 is 4 times 3, 4 times 3, but we have C2 here, so we need to substitute it. So we have 1 over 4 times 3 multiplied by our C2 is 0 all over 2 factorial. So our C4 is CO all over 4 times 3 times 2 factorial. That leaves us with 4 factorial. Now is n is equals to 3. N is equals to 3. We have C5 is equals to C3 all over 3 plus 2 is 5. Now is 5 times 4. So we have C3 here. Again, we need to substitute it. 1 over 5 times 4 times C3 is C1 over 3 factorial. So that will lead to C1 all over 5 times 4 times 3 factorial is understood as 5 factorial. There. Next is n is equals to 4. If n is equals to 4, we have C6 is equals to C4 all over 6. 4 is to 6 times 5. There. But we have C4 here. So again, substitute. 1 over 6 times 5 times C0 all over 6 times 5 times 4 factorial. Let's leave us with C6 is equals to C0 all over, let's do that 6 times 5 times 4 factorial is 6 factorial. So next is n is equals to 5. Now, if n is equals to 5, we have C7 is equals to C5 all over 7 times 6. But we have C5 here, so substitute. 1 over 7 times 6 multiplied by, if our C5 is C1 all over 5 factorial. And that leaves us with the answer of C1 over 7 factorial. And we have already found the multiple numbers of n, so now we can substitute it into our first equation. It's y. So our y is CO plus C1x plus C2x squared plus C3x cubed C4x fourth plus C5x fifth and so on. So let's just substitute. Group 0 C1x, we have C2 here and we have C2 here, so we need to substitute our C2. Our C2 is C over 2 factorial times x squared plus our C3 is C1 over 3 factorial x cubed plus our C4 we have C0 plus C0 all over 4 factorial times x to the 4th, and our C5 is C1 all over 5 factorial x fifth and so on. So we can now group this because they have common COs and common C1s. First, I will group the COs. COs times we have 1 here. Let's leave us with plus 1 over 2 factorial times x squared. Plus we have here 1 over 4 factorial times x squared. And so on. And now is C1 plus C1. We have C1 is that leaves us with x plus 1 over 3 factorial x cubed, and lastly this plus 1 over 5 factorial x cubed, and so on. With this, as you can observe, if you look at the transcendental table, you can see that they have transcendental functions. And their transcendental functions are 0, 1 plus 1 over 2 factorial times x squared plus 1 over 4 factorial times x squared plus, and so on and so on. Its transcendental function is push x. And now our C1, and this leaves us with this transcendental function of x plus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x cubed, and so on, is hyperbolic sum x. And that is how we arrive at transcendental function from a DE solution.